I'm Brian Staten, Project Manager at Robust Haven, and we designed the transmission control shift module. This is LeBlanc Meneses, our programmer, and then back here we have Jason Scher, the designer and creator of the PCB board, and also helped me integrate all the hardware. Alright, right now I'm going to walk you through the hardware integration demo for the transmission control module. Right here, made out of a drill box and painted black, we have our demo box. It basically simulates the transmission, and we're able to output all of our various signals to the box and have it basically indicate, what state the transmission would be on. And also we can change the way the transmission reacts to those outputs to simulate things like what gear you have it in and so on. I'm going to walk you through the different switches, buttons, and dials. Right here on the left side, these three switches simulate the pressure switch assembly in the transmission. And right down here we'll show you off of the actual transmission we're simulating. It's this device right here, and this is normally flipped around and laid over the valve body. And basically, depending on what gear you have the car in, overdrive, drive, manual 2, manual 1, neutral, park, or reverse, it'll push up on specific buttons, and it will output that logic onto 3 lines. It uses binary logic to tell you which of those which of the 7 gears that you're in. The other 2 lines go to a thermistor, and basically it's going to tell you the temperature of the transmission, if it's warmed up or if it's overheated, and we simulate that with this potentiometer right here. The car has a brake signal to notify any electronics that the brake has been applied, and that is this toggle switch right here. Up means that the brake is not on, and down simulates someone pressing on the brake. Right here we show you what state that the shift solenoids are currently in. We have shift solenoid A and shift solenoid B. That's the 2 shift solenoids right here. And it's going to represent 4 stages. Again, in binary logic, we have on and on is 1. So currently we're showing that we're in gear 1 in overdrive. And if it was going to go to gear 2, then you can just look on here and say, okay, it's going to be off on. So you'll see that this will go off and this one will stay on. For third, they'll both go off. And for fourth, you'll have on and off. Right here we have our line pressure. It's PWM signal. Goes to the line pressure solenoid exhaust valve. Right here you see the line pressure on the transmission, and it's going to take a PWM signal on this 4L60E transmission of 0 to 60% duty cycle. Since it's normally on, what that means is a low PWM duty cycle, so this light basically being off would represent the highest line pressure that you can have. And then as we send a larger and larger signal to it, say 60% duty cycle, the maximum, you'll see this light brighten to its maximum potential, and then basically that's simulating this having the lowest line pressure that it possibly can have. And the reason that you want to have a low or high line pressure and want that to dynamically change is because you're basing it on where the throttle is at that particular time. So if someone is in a car and they lightly press on the throttle and they're taking off very slowly, well then you would want low line pressure so that you don't get a real hard sturdy shift and basically squelch the tires every time you're taking off, real slow. But if you goose it and press the throttle all the way to 100%, you want the clutch packs to have enough pressure on them so that they don't slip. So you don't want any slippage to occur. The TPS that we're talking about, the throttle, is being simulated with the power supply right here. 0 volts is it not being pressed at all, and then going all the way up to 5 volts is 100%. This right here is another pulse width modulated solenoid, your 3 to 2. 3 to 2 downshift solenoid. This is normally 10% duty cycle, which you can see right now. It probably doesn't show up on the video, but it has a faint glow to it. And anytime it's not in first gear, it'll go to 90%, so it'll be in its brightest state in 2, 3, and 4. This is to cushion the downshift from 3rd gear to 2 gear due to someone pushing on the throttle really hard and making it do that downshift. It's to let the engine adjust to the new RPMs that are going to be in second gear. This is the TCC solenoid, which is located in the front right here, and what that does is it actually locks the transmission to the engine mechanically so that there's no slippage occurring through the torque converter. So this one, whenever the light comes on, the transmission is locked up. You only expect that in fourth gear when there's not a large change in speed, and the only other time is if the engine has indicated that it's overheating, and it's going to force it down to third, and either pulse the TCC or keep the TCC on to help cool the engine down as quick as possible. Right here you can see from the side, this is the transmission plug that actually goes to the transmission, which is where all these wires are coming from. So that's it right there, the wiring harness, real clean. These other wires that you see are wires that are going to go to various parts in the vehicle. You have basically a negative line that's going to go to your battery, a positive line that's going to go to your battery. You can see the power supply actually does run through runs through the TPS plugs. You can see our VSS signal right here going to the signal generator out a 100 hertz sine wave. This right here is what's going to produce that signal. It's going to be outputted with this one line right here. One is grounded, and it's going to go a sine wave that's always high. And every time this tail shaft makes a revolution, it's going to make this output 40 pulses. So you get 40 pulses per revolution of the tail shaft. The tail shaft is tied to the rear axle through your rear gear. And so if you have like a 411 gear in your back of your truck, that means that the axle is going to have to, or it means the drive shaft is going to have to make 4.1 revolutions per revolution of the rear axle. So that way you're able to convert a whole lot of turning into more power and slower turning, so you can get a lot of powers to the rear tire. You can see our VSS signal right here going to the signal generator, and the distributor plug. It runs through the distributor plug, and then right over here is the throttle position I was just talking about, that the power supply goes to. And these are unclean signals and couldn't be hooked directly to the microcontroller. So we are inputting signals that are higher or exceed the limitations of the microcontroller pins. So all this has to go through signal conditioning, which if you can get in on this and show that we have a board right here that all inputs will go through and be filtered, like filtering sines or pulses into nice square waves for the microcontroller's TPU channels. And then also all outputs are going to be triggering BJT and MOSFETs to source the current from somewhere besides the microcontroller, because it obviously couldn't drive a 1 amp solenoid. So these this system requires a lot of amperage to control that many solenoids. So that's that, and you can see this is where your interface is going to hook up to. You have the controller hooked to the microcontroller. Later on, the microcontroller unit will be moved over to the PCB so that it is one unit. And we'll start walking you through the states now that y'all have an understanding of what to expect and what we hope happens. Right now you can see that we're currently in gear 1 by both lights being off. And if I jump here on the signal generator and we start increasing the speed, you can see that it went from first gear to second gear at 370 hertz. And this is the actual pulses that are coming off of the tail shaft of the transmission. And there's 40 pulses per revolution of that tail shaft, and then it drives the rear axle with the ratio of the rear gear that the user currently has installed on their car, and then that will get converted into miles per hour, taking into account, converting to miles and hour, and then the circumference of the tire, the diameter. We'll show you the rest of the states just to show they all do work. And there you see third gear occurred, and then fourth gear. So that is it's shifting all the way up and then all the way down. And now basically we'll show you that it does use both the upshift and the downshift charts, and you can change at what point it does upshift and at what point it downshifts, and that's totally configurable through the desktop. And it's also a necessity so that you don't have an exact shift point that occurs for the upshift and the downshift, because if you drove around that speed you would have flutter back and forth between those two gears. So right now we're using basically around like 5% difference value from the upshift and the downshift. So if we find out exactly where an upshift from first into second, it happened around 330 hertz, and if we decrease, you see we have to decrease significantly before it drops down into first gear again. And this occurs for all gears, so we'll go ahead and around 1,000. So if we make it just go into third gear, which you saw right there, and there's no delay here, I mean it occurred right then, you can see that we had to drop down a whole 100 hertz before it actually went back to its previous state, and that occurs for all of the gears. So you can see that. Now basically we're going to show you that not only does it shift based off of the vehicle speed at the time, but this is also directly related to whatever the TPS is at that time, the throttle position sensor. So you don't have just particular shift points for each gear, but you have a multiple of 10 shift points per gear. And out of those 10, it's broken into 10 different TPS values. So you could have a shift point from one gear to another at 10% throttle, at 20% throttle, at 30% throttle, and so on. And we'll show you if we get this to go into fourth gear. We'll just show you one time how it works and try to get it to do a massive shift down. So if to simulate someone basically goosing the car, giving it full throttle. So you see we can go down here to about 1.476 before it ever shifts down, and right now it's maintaining in fourth gear, and the throttle is this car obviously wouldn't be going this fast if you had zero throttle, but if we started easing the throttle down, you'd see that it jumps down to third gear, and then if we floor the car, we're not able to get it to shift all the way to second, but if you had your shift chart configured for like performance driving or strip driving, you would see that it would occur. So let's try another configuration that we have stored on the controller. This comes in handy for exactly these things, like if I was driving on street and I wanted a smooth ride and didn't want real sturdy shifts or anything, then I can have it in that setting. But stored on the controller is a second configuration, and you can basically get to that configuration easily off your dash by using the toggle switch. And then we're running a different set of user parameters. So now we'll see where fourth gear currently goes off, and it's around 1.2. And then we'll try it now and turn the throttle all the way up. That's third gear. And then you see it shift all the way from fourth gear to second gear with our new configuration file. So this is more for like you performance users that really want your car to just drop to a low gear, have a fast hard takeoff. That is your particular configuration. So we can also show you right there that we can access two different settings. Your line pressure right here, you might have noticed that this light was dimming and brightening as I was messing with the TPS. And again, that's your line pressure, and it's directly related to the TPS. And again, the user is able to configure the line pressure to react however they desire to the throttle position. So you could have a setting for normal street driving where your line pressure is a nice linear curve, or you could have it for towing where you'd have more of a logarithmic curve, so that you have more line pressure at lower throttle speed, so you'd be able to tow things and whatnot without the clutch packs slipping. So right now, you can see with zero throttle, it's showing you that there's not very much line pressure because we're giving it a big PWM. And then as we increase the line pressure to maximum throttle, you can see that there's a lot of pressure now in the transmission because we're hardly letting any fluid past. So it's all building up, causing a high line pressure right now. The 3 to 2, right here, we can show you that the 3 to 2 is off in first gear, just like it's supposed to be. And then as soon as we switch to any other gear, second, third, and fourth, the 3 to 2 goes to a 90% PWM. And that's exactly what we would expect. Okay. Set the temperature for the car right now. Okay, right now the temperature setting for what it is, we're representing the engine as cold. And if we go into fourth gear, you'll see that the TCC is not applied. And you might at first think that's a problem, but that's because the engine is too cold and locking up the TCC. When the engine is cold, like on a windy day and your car hasn't had significant time to warm up, that could cause damage to the vehicle. So after it gets to whatever temperature that the user sets in the user parameter interface, you'll see that the TCC does come on once the vehicle's warmed up and is in fourth gear. If we go out of fourth gear, you'll see that the TCC goes off again. If we go back into fourth, you'll see that the TCC is applied. If there's any brake indication to the microcontroller while it's in fourth gear, it's going to unapply the TCC because it's going to signify a decrease in acceleration. So you don't want the transmission locked straight to the engine while you're changing speeds drastically. So if we take our foot off the brake again, the TCC comes on. One thing that is not implemented in the code right now that is currently not working is also any significant change in speed should unlock the TCC. So even if it's in fourth gear and the brake's not detected, if we change the speed and basically simulate a large acceleration or deceleration, then the TCC should unlock also so that damage does not occur to the transmission. All right, this is the LabVIEW simulation that we created to analyze all the logic of the microcontroller and what our program is doing as we developed it. This has been very beneficial because, as you can see, we can show all of our code running on the LabVIEW. It does have the implementation of the torque converter unlocking when there's a certain degree of change in speed detected on the vehicle. So right now we have the vehicle going 87 miles an hour and the torque converter is on because it's in fourth gear and we're not changing speed. And then if we change speeds, as you can see, the torque converter stays on. And we're changing 86 miles an hour to 85 miles an hour. Let's see if we can. There's 85 miles an hour, and you can see that the torque converter stays on. So I mean, that's like if you're driving down the road, obviously there is going to be some changes in speed going up slight inclines and declines, and the car not being a perfect machine. But if we change the speed drastically, so we drop down, but we stay in fourth gear, you can see that the torque converter does go off. So any large changes in speed are going to make it unapply itself. But if I leave the speed again, where it's at, so it's at 82 miles an hour, then it's going to come back on, if the speed stays within, whatever parameters that the user has programmed into it at that time. And so it takes about, I think, 11 seconds, but obviously you can make it a lot shorter if you want. It's just a dial on there. And as you see right now, the light came back on, the torque converter is applied again, and large change in speed made the torque converter unapply itself again. So we'll put it back, actually we'll start in fourth gear, and if you look over here on this chart, I am switching it from overdrive into drive by off, off, on, which is right there. And now we're in just regular drive, which only 3 gears are allowed to us. And you'll see that it's in 4th gear. You may think that something's wrong, but actually we want it to stay in 4th gear, so if someone accidentally drops it down to drive, it's not going to damage the vehicle. But if you lower the vehicle speed down enough so that it will go into 3rd gear, then you'll see that it is locked there. Because now, I mean, you would be hearing your engine constantly speeding up, and hopefully the user wouldn't cause damage to their vehicle by, you know, having it in 3rd and just keep on accelerating thinking that something's going to happen. But no matter how fast we make the car go, it's no longer going to go into 4th gear. But all other gears still work as expected. And this goes for all of the other ones. Basically, the only difference is in manual 2 and manual 1, we do not hold the gear, because it's assumed that if someone puts their car all the way from the top in drive down to manual 2, then it was from a stop. I mean, it's someone that's expecting to tow something like a boat or trailer, so it will go directly to that gear. And also, it wouldn't make any sense to hold the gear, since in manual 1 and 2 and the 4L60E transmission that we are simulating right here, it mechanically overrides whatever the shift solenoids are telling it anyway. So we're basically playing catch up with it in drive 3, but in manual 2 we don't bother. Now, if we go back to 4th gear and have to take it out of drive, and then you'll see we can shift up to 4th gear and the TCC comes on. If I make the engine cold, you see it goes off. Now the opposite, the extreme, is if the engine overheats, and we'll simulate that by turning it counterclockwise, and you'll see if it overheats, the car goes out of 4th and into 3rd gear, so the transmission is causing less friction and producing less heat, making your RPMs shoot up on the engine, but at least your transmission has time to cool down. And then also your TCC, even though before it was not supposed to come into 3rd, now it's being forced on, which you can see right here. And it's staying on for a long period of long duration, and then it'll go off briefly for a couple seconds and then come back on, which we thought would be a good idea to notify the user, because the engine would be dropping and then raising in RPMs. But the actual client that we're making this for wants this converted so that it actually stays on, and luckily that's easier to do, so we just have to take a couple lines. We'll show you that it shifts based not only on the VSS signal, but it also shifts on the distributor signal as well. And let me lower this down so that we can put it back into 1st gear. And basically we're doing like 4 or 5 miles an hour now. And then this power supply is outputting twice this value, so it's outputting 10 volts with a pulse signal, so it shoots up real fast. And this is to simulate the similar type signal to what you would get off of a raw ignition coil, and it creates a lot of noise. It's being filtered out and into nice clean square waves for the microcontroller. And basically this is showing you exactly what the RPMs of the engine are. It's not being calculated from the VSS. It's straight off of the distributor. And the one thing that we're using this for is for a max rev limit. So if we set a max rev limit through the user interface, the graphical user interface that we program this with, then you could set a value like, say, 4,500 or 5,000, and you know that your engine would be damaged at any RPMs higher than that. Well, then you can set that, and then any time that it's detected that your distributor signal is outputting higher than what your max rev limit is, it's going to cause these to upshift. So we're going to go ahead and do that now, and I know that we had it set at like, I think like around 4,800 RPMs. So we'll go a little bit higher than that. I think 500 hertz would be around 4,800 or 4,900 RPMs, because it's going to be your distributor signal divided by 4 times 60 to get to revolutions per minute. So you'll see it went from first to second, and then it went to third, and then there's fourth. Now you would think that maybe there's a bad delay or something in the microcontroller, but that's actually something we had to implement. I mean, the microcontroller is super fast with this easy type logic. So what would happen is if the max rev limit was reached and it was currently in first gear, well then as soon as we raised it to 500, it would analyze it, shift it to second gear, analyze again, shift it to third, and it'd be so fast that your shift solenoids wouldn't even have time to respond to that. So you would basically get a direct shift from first gear all the way to fourth gear. So there's basically a wait 3 seconds before it analyzes it again and does that shift based on the distributor. So we'll show you again that it shifts, and then your RPMs in your car are dropping because your gear ratio has changed, and then it does the analyzing again, and then you see it wait, and then you get the fourth gear. During this time, your VSS speed would increase to hold it in that gear. So if I had it at 3,000 now, you sped up to that. Then after your RPMs drop because you're in that new gear, your car would be held in that new gear. And that's our transmission control module.